Good day, everyone. So, we will continue with our next lesson, that is on finite difference method. So, in this chapter, we will focus our finite difference method. So, finite difference method is also known as um, FDT. So, finite difference method is also known as FDT technique. Right. So, we will be focusing this on temperature difference problem, multi-dimensional. So it will be multi-dimensional. So this can be either in 1D, 2D or 3D. But we will be focusing mainly on the 2D problems, right? So that's our topic. So you can see here multi-dimensional steady state conduction. So again, it's a heat transfer problem. So we have many practical problems. Temperature and heat flows are functions of 2 or 3 coordinates. So you can either have it in 2D or 3D. Such cases occur when the boundary is non-uniform. So you can have problems related to heat flow through a corner section where 2 or 3 walls meet, conduction through the walls of a short hollow cylinder, or heat loss through a buried pipe. Right. So all this involves multi-dimensional steady state conduction. So now when I talk about steady state here means no change with time. So there is no transient heat transfer involves. So steady state means no change in time. So you can see here, so you can solve a problem, right, in two-dimensional and also three-dimensional, either by using analytical, graphical, analogical. And for our finite difference technique, we will be focusing on this part here, right? So you can see in the notes here that we have problems that can be solved using analytical, can be solved using graphical, can be solved using analogical, and also by numerical methods, which will be the focus of our study. Right. So finite difference methods using computers is often the best choice. So here we will see that why we need computers. The reason is it involves a lot of nodes, and these nodes need to be solved by a computer program, and these nodes can be as many as a few 100,000 nodes. Right. So it's not possible to do this by hand, so you can only do it by computers. But in class we will learn how to solve finite difference method by solving a problem which has only about 4 nodes, so that you understand the algorithm behind it, and then you can apply the same algorithm to solve problems using computers later on. Right. So you can see here, so this is the temperature profile. So if you want to calculate what is the temperature here and how it changes from this point to this point, right, so you can actually use any of these methods, and then you'll be able to plot out the temperature profile. And this is done at different pressure conditions, and you will see that the temperature changes from almost 200 degrees Celsius to 550 degrees Celsius, and it is illustrated here in different colors. So the idea is how to plot this temperature profile by using all these methods. All right, so it can either be in 2D or 3D problem. So we also know Fourier's law of heat conduction. So from Fourier's law of heat conduction, you get this rate of flow per unit area, or we call it heat flux. All right. So you have both in the x and y direction. So temperature we know is a scalar quantity, it's not a vector quantity, but this heat flux is a vector quantity because it depends on your temperature gradient. And this temperature gradient, as you know, it has got a direction, it goes from hot to cold, right? So because of that, heat flux becomes a vector quantity, right? So this is analytical solution problem, right? So you can see that this is again a 2D problem. So what they want is they want to plot these temperature profiles, isotherms we call them, right? And then you also have these heat flow lines. So how they interact, so it's given here. This is part of your analytical solution again. So you can actually go through this on your own. We will be not focusing on this, all right? So the idea here is we want to solve for 2D steady state no heat generation problem by using these this conduction equation, where this takes care of the x direction and this takes care of the y direction, and this is equals to 0 because we say that there is no heat generation. If there's a heat generation, this will not be equal to 0, which we will see in a while. Again, you change it, right? And this is what you get, and then by solving this, and you will have this equation. So you use variables are separated since neither side can change as x and y vary. Both must be equal to a constant, say I square or delta square, no? Right? So continue, and then you get this by solving them. You have this equation in x and y. So if you want to solve them, that will give you analytical solution, which will give you a data graphical output in this form. So graphical method is also there, right? So it's has now been superseded by computer solutions. So you can see that the rationale behind graphical method comes from the fact that lines of constant temperature must be perpendicular to lines that indicate the direction of heat flow, right? So you can actually draw a flux plot by constructing a network of isotherms and heat lines as what is shown here, right? So this is graphical method. You also have analogical method, right? Situations where two or more phenomena that can be described by the same equations are mathematically analogous, right? So here you have one we call thermal resistance method. So here what you are doing is you are using your 2D Laplace equation, and this is you are making it analogous to the electrical potential equation. So you can see that they are basically the same, but here you are talking about temperature, here you are talking about electrical potential or electrical field, right? So you can use this analogical method to solve problems in um, uh, thermal engineering or heat transfer, right? So now we go into our finite difference. So in our finite difference, we will be focusing on this as our numerical method. So you have numerical method based on finite difference technique, generally suited or ideally suited for systems of more complex geometries by means of high-speed computers. All right. So you can either do it for 2D or 3D system, right? So if you have a 2D system such as a solid or constant thickness B, you can divide them into equal increments in both an x and y directions. So for an example, if you have a square, so this is the square. So this square, we say that it has got certain thickness. So you have certain thickness, and this thickness is given by B, right? And then you have some lengths to it, right? This is the length and this is the width. So there is the total width. So now we want to know what is the temperature here, T1, what is the temperature here, T2, what is the temperature here, T3, and what is the temperature here, T4, right? So what you can do is you can actually divide them in both x and y directions. So you can have the same profile, right? So we have this is x direction and we have this as y direction. So we can actually divide it, right? So we make this and we get our nodal points here. So these are the nodal points that is of interest to us, and we can then apply our mathematical equations to each of these nodes and then try to solve them and then obtain the answers that we want, let's say for these temperatures T2, T3, T4. Of course, you need to know the boundary condition. So all the temperatures here need to be known. All the temperature here need to be known. All the temperature here for all four nodes need to be known, as well as these four temperatures, right? So once you've got that, then you will have four equations, right? Because what you have is you have four nodes solving for T1, T2, T3, and T4. And then we will learn how to solve this so that we can get it. Now bear in mind the subdivision here. So when you divide this into smaller subdivisions here like that, the length from here to here and the length from here to here should be same. So in other words, your delta x should be equal to your delta y. So this is your delta y, right? So subdivision, and this is your delta x. You can divide it further into a very fine part again. So if we have the same geometry again, so we can actually divide this into much more smaller components as well, right? So if you divide it into smaller components, of course your delta y and delta x changes. So this is what you get, and you get many more nodes. So these are your nodes again. So you have all these nodes, you can continue to get all the nodes, and then this becomes your delta x, and this becomes your delta y. Of course, this is much crude because you got a bigger element here. This has got a smaller element. This will give you a much accurate answer. So it all depends on your computational capability of your computers, on how best you can solve this nodal problem by using the program that you write. So this is our element again. So as what we've discussed, so we have in the x direction and also the y direction as shown here. So both the x and y directions are given. So you have your nodes, right? So all your nodes, and then your subdivisions in x, dx, and dy, and this gives you the thickness, right? So the thickness. So these are all nodes. So all these are your nodes on the element. So you can subdivide your whole element here into a small nodal system, and then what we want to do is we will apply our equations to each of these nodes, try to solve this, and then using this answer try to find the answer for the subsequent node and subsequent node and subsequent node. So that is how we solve problems in numerical methods using finite difference technique. So here we have the finite difference numerical methods, right? So if you look at the slide here, in the absence of a heat source or sink in the system, the rate of heat flow toward the nodal point must be equal to the rate of heat flow from it in steady state. So all the heat is coming in into this nodal system, and if you notice that we have a coordinate system that we have here, so Mn is this one, a node right above it is Mn plus 1, a node right below it is Mn negative 1, a node that is on the right is M plus 1n, and the node on the left is M minus 1n, right? For an example, if you have a coordinate of 2, 2, so the node right above it is coordinate 2, 3, the node below it is coordinate 2, 1. The node towards here is coordinate 1, 2. And the node towards here is coordinate 3, 2. Right? So this is the central node. And then what you see is the node this side, the node towards this side, the nodes towards this side, and the nodes towards this side. So what we want is, we want to know when we are talking about this node, the nodes that are affecting us are right above it, on the left, at the bottom, and also on the right. Right. So this is how you basically label your node. Right. So differential equations are there. So I'm sure you've done this before. So your differential equations, limit delta x equals to 0. So this is from your form 4 and maths, right? So if you, instead of taking the limit, right, you can use the following approximation, and then you end up with this equation, right? So we will now apply this equation into our finite difference technique. So remember our element here. So here we are talking only in the x direction first, right? So the one that is here is m minus 1. The one that is towards this side is m plus 1. And this green line actually tells you the midpoint of this and the midpoint of this, right? And correspondingly, you will get your temperatures, right? So these temperatures are given, and delta x is given with the length that you have divided by the uh, uh, what you call that, the divisions that you are looking into, because it's m sections of equal length. So this is only in x direction, so we use m. And if you apply the differential, this is what you're going to get, right, for m minus 1 and m plus 1. And if you do go for second derivative, because the earlier was only first derivative, and now we are going for second derivative, apply it, and this is the final equation that you're going to get, right? Now we do the same thing for y direction. So earlier in the previous slide, what you had was for the x direction. So this is for the y direction, and you will end up with this equation. Now remember, I've shown you earlier we had this equation here, right? So now we need to add them up, equals to 0. So we have finished this individually, we have finished this individually here. All right, now we need to add them up. So add them up and then equate it to 0. So why 0? Because we say that there is no heat generation. So if there is no heat generation, then automatically this becomes right. So now if you look at this, this is doing the same problem again, and you include the heat generation. So your heat generation is given by this formula, right? I mean this symbol. So this is the heat generation. Unit is watts per meter cube, right? So K is your thermal conductivity. So this is a property of any material, thermal conductivity. So if you have heat generation, then this terms comes in into the equation, right? So if you don't have heat generation, then this is ignored, right? But if you have heat generation, then you got to add this in, right? So this is still equals to 0, but if you take this out, so if let's say I want to take this whole term out here, so then it becomes negative q m over k, right? So then it's this entire term equals to negative q over k if you take this out. So you can do it for this for 2 dimensions. So this is for 2 dimensions. So you have this part, this part. This is there because we have heat generation. So when you have heat generation, you include this term. If you don't have heat generation, then you can ignore this part, right? So for this we have already defined. So we get this part of the equation based on what we've done, and then for this is this part of the equation, right? And this is basically you shift it out from here to this side, you get negative q mn over k, right? Now bear in mind this and this is essentially the same, delta x equals to delta y, because we are using the same divisions. So your delta y and your delta x are same, right? So that is why you get a square here. And because these two are same, because this and this are same, you can add all these terms in. So this stays on its own, this stays on its own, stays on its own, stays on its own. But if you notice, this is negative 2tmn, this is negative 2tmn. You can actually add them up, it becomes negative 4tmn. And this same, so you can actually group them up together, and then because here is division, you can multiply it with this part here, and that will give you this equation. So this is the equation that you can use to solve finite difference problems in the uh, problems related to heat transfer where you want to find the temperature, right? So remember this formula, so it's not that hard. So what you want is you have the mn here, this is mn plus 1, this part here is m plus 1 n, this one here is again m n minus 1, this is m minus 1 and n, right? So these are the temperatures. So if you look at the formula, it is nothing but you add this plus this plus this plus this minus 4 of this equals to this if you have heat generation. If there is no heat generation, this is equals to 0. So this entire term then becomes 0 if there is no heat generation. If there is heat generation, then you need to include this. So we will see in our next examples on how to use that. And then if you want to find your heat transfer, you can use this Fourier's law of heat conduction for x direction and also for y direction. Right, so this is your finite difference expression for all the nodes that you have, all right, towards the central node. Okay, so you can do that and you get this equation again. All right, so that was done by solving problems related to your transfer. So as you can see from the diagram here, right, so you have a plate, all right, both in x and y direction. So how the temperature is being distributed, so you can actually use finite difference technique. You can actually divide them into nodes like this. right? Equal nodes, so you can divide them, and then you can have this as well. So lines should be straight, right? So find the values here, right? So all these nodes you can find the values, and based on the values that you obtain for all the nodes here, then you can draw this temperature profile. Of course, if you can refine it further, you can make the mesh smaller. So the smaller the mesh, the better it is. But you can see if it's smaller mesh, you will have many more nodes there. So your nodes will increase, but this will improve your accuracy. Of course, you will need to have a very good computer software to solve that, right? So you are applying some equations, right, for the temperature at various nodes. So all these nodal points here, you can apply your equations and solve it, and then get this temperature profile. Right, now let's look at this example. So this example is basically asking you, it is given a square plate, small plate 1 meter by 1 meter with a K value of 10 watts per meter degree C, has one phase maintained at 500 and others are maintained at 100, right? And then you're asked to find temperature at various nodes and heat flow at the boundaries. So what you need to do is we can actually divide this into smaller elements like this. So when you divide them, so these are the nodes that you get. So all these nodes are there. So you will see that you have this many nodes, and this temperature is what we are interested with. We know the temperature of these nodes, right? So these nodes temperature is 500. For these nodes temperature is 100. These two nodes temperature is 100. These two nodes temperature is 100. So what is left is we want to find these four temperatures, and how are we going to apply our finite difference method modeling to solve problems related to temperatures as shown in this problem, right? Of course, these values are given, these are your boundary values given to you, and they will be helpful to you to solve the problems that are given as shown in this example. So this is how you subdivide your element. So if you look at it, the entire length was 1 meter. So this was 1 meter, and this was also 1 meter, and you have subdivided it into three subdivisions in the y direction and also three subdivisions in the x direction. And as a result of that, you get these four nodes that you don't know the temperature. You label it as T1, T2, T3, and T4. Right? Now, if you look at it, you have to check the internal node as well. So the internal node is shown here. So this is your internal node. So you have full internal node here for T1, you have full internal node here for T2, and you have full internal node here for T3, and you have full internal node here for T4. So when you have full internal node, then you can apply the equations directly. Now let's look at this node. So do you have full node here, full internal node? You will see that this is only 1/4. So it's not full, not full. So you can't use the equation that we discussed earlier. Now let's look at this node. So is this full node? No, it is again half a node. So this, if this node was, but we are lucky because the node value is given. Just say that this value is not given, then we can't use the equation directly. We've got to solve this using energy balance. So similarly, same thing for this node. This is not a full node, this is only half node. For T1, T2, T3, T4, it is confirmed that all four of these are internal nodes. Then we can use the equation directly to solve this. Right? So this is what we get when we apply this equation. Now look at node number 1. So remember, this is 500. This part here is 100. This is 100. This is also 100. Now if you want to apply this equation to node number 1 here is nothing but you take this 500 plus 100 plus T3 plus T4, right? So that is for all of this, and then minus 40M minus 41, and then because there is no heat generation, so that is equals to 0. So similarly for node 2, you take 500 plus T1 plus T4 plus 100 minus 42 equals to 0. For node 3, you take T1 plus 100 plus 100 plus T4 minus 43 equals to 0. And then you have for node 4, you take T2 plus T3 plus 100 plus 100 minus 44, alright, based on this, and you will get this equation. So now you have 4 unknowns and you have 4 equations. So how are we going to solve this equation? So we can use a technique called Gaussian elimination, so which we will discuss in our next. So you change it into this format, right? So we rearrange the earlier equations, so we get this, right? So you will see that your T4 here was 0, so we have not included that. Now we have to change this into a matrix form, right? So this is the matrix that we've got, right? So if you remember your matrix, negative 4 times T1 plus 1 times T2 plus 1 times T3 plus 0 times T4 is equals to negative 600. So it's nothing but negative 4 times T1, the first row here, plus 1 times T1 plus 1 times T3 plus 0 times T4 equals to negative 600. And you can do the same for this row, you can do the same for this row, and you can do the same for this row, and you will get the previous equations that we had. Now the idea here is to use Gaussian elimination. So in this triangle, we want to make all these elements to be 0. So we want all of this to be 0. So at the moment we have only this as 0, this as 0. Now we want to change this to 0, this to 0, this to 0, and this to 0. So how to do that is, one way to do that is you can actually multiply something here for this row, and then you either add or minus with the row above or row below to make this 0. So again, as I said, the idea is this triangle, everything should be 0. So let's look at this. So this is the Gaussian elimination method that we are discussing. So again, I would like to highlight, so we want this triangle here to be 0, right? So how to make it 0? Let's look at the steps. So the first part here, what we do is we multiply this row with times 4. So if you multiply everything here with times 4, this is what you get. 4 times 1 is 4, negative 4 times negative 4 is negative 16, 4 times 0 is 0, 4 times 1 4, and then you also multiply with this, so you get negative 2400. And next step what we do is to make this 0, whatever value that we get here, we plus with this one. So when you plus with that one, automatically this becomes 0. If you plus this, then this also you need to do the same thing. And same thing with this, you add it, and similarly for this also add it up, and finally not forgetting this one. So add that up, and this is what you get. So you see here we've already got 0 here. So next we attack this row here now, right? So remember our triangle, we want everything in this triangle to be 0. This is accomplished. Now we want to make this 0. So what to do that now? So again same thing, you can multiply this with 4, the entire row. You can multiply by 4, and then once you got 4, and then you add it with this, right? So if you add 4 times 1, 4, 4 plus negative 4 is 0, so this becomes 0. And similarly you do this, add with this, do with this, add with this, do this, add with this, and not forgetting this, you add with this, right? And this is what you get as a result of that. And then again we are happy, everything here is 0 0 0. Now we want to change this to 0. So how to change this to 0 now? What we can do is we can multiply this with 15, the whole row with 15, and then add with this. So 15 plus negative 15, 0, automatically this is 0. So now you don't add with this row, because if you add with this row, this will become a number again. So what you do is, any number you multiply with 0 is 0. 0 plus 0 is always 0. So you got to add with the second row. The result of that, you get this equation, right? And finally, again, you multiply with 15, you get this as 0. So we are now reaching our target of getting everything in this triangle to be 0. And what is left now is 16. So again, we need to multiply something here and then add with this row. So anything times with 0 is 0, plus 0 is 0. So this and this also maintain 0. Now what you need to do is, you need to somehow convert this into 2 to 4. Because 2 to 4 plus negative 2 to 4 will give you 0. So the only way to do that is to get this equation. So you multiply this, and then finally you get everything here as 0. So Gauss elimination allows you to do that. And then now you can actually apply this. So remember, this is 0 times t1. So the equation is 0 times t1 plus 0 times t2 plus 0 times t3 plus negative 720 times t4 equals to negative 108,000. So this way you can find t4. So once you found t4, from here you move up to one more level. So from this level, what you're going to get is 0 times t1 plus 0 times t2 plus negative 224 t3 plus 64 t4 equals to negative 24,000. So T4 is found earlier. Now you substitute it here, you can get what is your T3. And you do similarly for this row and this row, and you will get all the answers for your T1, T2, T3, and right. So this is the matrix. Solve it. So these are the equations as what we've discussed. You start from the bottom row and you go to the third row, second row, and the first row. So once you got T4, you substitute here to get your T3. Once you got T3 and T4, you substitute here to get your T2. Once you get T2, T3, and T4, substitute here to get your T1. And that is how you get all the values that you want. Once you get all the values, you can substitute it here. These are the values that you were looking for. And for this example, they've continued by finding out the heat transfer. So for heat transfer, you can use this formula, substitute all the values, you will get all the Q's you are looking for, right? These are the values that you want. Heat flowing into the plate is 9,000 watts per meter. Heat flowing leaving out the plate is 9,000 watts per meter. So it's steady, and all the other values are correct, right? Now another point here is, if you look what we've discussed based on our example earlier, if you look at note number 4 is an internal node, because you have a full node here. So you can use the equation directly. Now look at node number 6 again. Node number 6 is a full node, so you can use the equation again. So this is also a full node. This is also a full node. So you can use the equation directly. Now what about node number 3? Node number 3 is not a full node. Node number 3 has got only half a node. So you can't use the equation into this problem directly, but because you have insulation and node number 3 is a half a node, what you can do is you can actually use a mirroring technique. So imagine you put a mirror here and you reflect to this side, and now you get a full node. Now because you have node 1 here, node 3, because of mirroring technique, this is mirrored here. So this is also 4, and now you get a full node. So for node 3, if you apply the equation, no heat generation, T1 plus T4 plus T5 plus T4 again minus 4T3 equals to 0. So then you can apply this equation directly. But only if you have half a node and insulation, then you can actually mirror it, to use the mirroring technique to get the full node, right? Now look at node number 2. Node number 2 is half a node, but you don't have insulation here, so then you can't use this equation. right? This node again is only half a node. You don't have insulation, you can't, right? Now what about node number 5? Node number 5 is also half a node. So because it's a half a node and you have insulation, you can then reflect this, so you get T6 here, and this is your full node. Now what about this node? This node, if you see, is only quarter a node. So quarter, if you reflect, you will not get full node. So again, you can't use the mirroring technique for this, right? So this is some of the things that you need to know. Now if you have a node, right, so imagine you don't have insulation here, then you will have to use a technique called energy balance, right? So energy balance, so imagine if you have a full node, right? So this is your full node. So your node, central node is here. So this is your delta x, and this is your delta y. If you divide it into 2, what you're going to get is this is your delta x over 2, and this is your delta y over 2, right? So for the full length here, we label it as delta y, because this is only half a node, delta x over 2. Again, from the full, if you want to consider only the half, this is delta y over 2, right? So we will see how the energy balance is applied, right? So we come back to this again. So this is your energy balance, right? So again, without any heat generation. So if you remember our earlier node, so we need to sketch our earlier node that we were discussing here. So we will use, so we had, this is our node, and then here you had node 4, and then here you had node number 5, and then somewhere up here was node number 1, right? So you had this, and then this is the half node, okay? So we have only half a node. So what you need to do is you need to calculate out your heat transfer coming in here, heat transfer coming in here, heat transfer coming in here. So perhaps I'll draw it here again. So this is the half node that you have, right? So these are the number 4, node 3, node 1, and node 5. So we need to calculate the heat transfer from here, here, and here. Now bear in mind, so what we are looking for is what we want is this length is now delta x over 2. This entire length here is delta y, and this entire length here is still delta x over 2, right? So let's consider heat transfer from 4 to 3. So heat transfer from 4 to 3, so that is given by this, right? So this comes from the equation Q equals to K A delta T over delta X. So this is your Q dot, right? So we are looking for the equation. So now imagine your heat is coming from 4 to 3. So we use K. So this is K, right? K. And then we will come to this in a while. Now what is the temperature difference? So the temperature difference here is T4 minus T3, because direction is here hot to cold. So T4 minus T3. And if you see what is the length that is traveling, so from this point to this point, so this entire length is, this is half delta x over 2. So this entire length will be delta x. So that's why you get delta x here. Now we need to find an area. So for area, you need to look at this part here. So this part is nothing but your delta y. And then you need to look at the thickness, because area is this area. So you need to look at this area. So what is given to you is this area, delta y, and we want this area. So we assume that the thickness is of certain length, b. So we put here b first. So delta y times b, right? So that will give us the area in the y direction, and this is the heat transfer coming in from node 4 to node 3. Now consider the same thing from node 1 to node 3 again. So node 1 to node 3, you have to pass by this area, right? So this area, again, our k remains the same because same material. The delta t is t1 minus t3, right? T1 minus t3. Now if you look at it, so from here to here, the length is delta y. Length is delta y, right? So if the length is delta y, so we put delta y here. Now what about the area? So this area here is this line multiplied with some thickness here. So you need to imagine the thickness here. So this line here is nothing but delta x over 2. So you get your delta x over 2 times with b. B is something that we consider the thickness is to be b. So we are done with this part. Now we are left with another T5 to T3. So we will now go to our next example. So our next example is given here. So based on this example, so what you have here is steady two-dimensional heat conduction in an L bar. So for this L bar, you have total of 15 nodes, and out of these 15 nodes, node 1, 4 and 10 are on the insulation side. I'm sorry, node 1 and 4 are on the insulation. 4 only is on the insulation. 1, 2 and 3 is exposed to convection. So convection is given here. 1, 2, 3, 6, 7, 8, 9 is exposed. 8 is up to 8 is exposed to convection. Node number 9 is exposed to heat flux. Node number 10 to node number 15, the temperature is given as 90. So out of the 15 nodes, if you see, we know node number 10 to node number 15, they have temperature equals to 90, but node number 1 to node number 9 is not known, right? And then the division is given. So dx is equals to dy, which is equals to L, right? K value is given, thermal conductivity given, T infinity is given here 25 degrees C, this is by convection. H value, so convection heat transfer is 80 watt per meter square degree C, and now you have heat generation. So this is the value for heat generation, so you can't ignore this term now into the equation. So again, if you look at the equation, so for the equation, what we have is, we have node number 1, we want to check whether it's a full node or not. So node number 1 is not a full node, it's only a quarter node. So let's check for node number 2. Node number 2 is also a half node. Node number 3 is a quarter node. What about node number 4? Node number 4 is half a node, but because you have insulation, you can use mirroring technique. And then reflect this here. So this becomes 5, so you get full node. What about node number 5? Node number 5 is a full node again. And what about node number 6? Node number 6 is not a full node, it's a 3/4 node. Node number 7 is only half a node. Node number 8 is half a node. Node number 9 is only a quarter node, right? So you can use the equation directly for node 4 and node 5, but for all the node number 1, node number 2, node number 3, 6, 7, 8 and 9, you'll have to use the energy balance as what we've discussed in our previous slide, right? So for that, let's look at the solution. But before that, these are the assumptions, right? So you have heat generation from the volume elements by partitioning the region. You can see here. Node 5 is the only completely interior node. Consider the volume element represented, so you get a full size node. But we have another node, we can make it into a full size node because of the mirror technique. Right? So that is node number 4. So as discussed just now, this is only a quarter node. This is half a node, quarter a node. Node number 5 is the only full node. Node number 4 can also be made a full node because it's a half a node with insulation, so you can reflect it. Right? So these are some of the things that you need to consider. So if you have a quarter node, your dx is half, right? Your dy, this is dy half, this is dx half, right? So this is for all the bottom nodes, T10 to T15, you have 90 degrees Celsius, right? So that is known. We don't need to calculate that. Now let's look at node number 1. So for node number 1, so as we can see here, this is not a full node. This is quarter node. So we need to now calculate out where is the heat coming from into the node number 1. So for node number 1, we have heat coming in here. So heat coming in here is from convection. And then from this side, heat is coming from node number 2. And then from this side, heat is coming in for node number 4. Right? So let's look at the heat coming in to node number 1 from this section here. So this is convection. So convection, again, the formula is Newton's law of cooling, T surface minus T infinity. Or you can also have HA T infinity minus T surface, depending on which temperature is bigger. Right? Now since the heat is coming in into the element, so it will be T infinity minus the node temperature. So A again, so if you have a surface like that, so this is our length. So let's say delta x over 2. You need to then elongate this, right? So imagine you have certain thickness. So this thickness is B. So this is the area that is involved with the heat transfer. So it will be delta x over 2 times with B, right? Now we assume in this example B is equals to 1. So if B is equals to 1, so then you have only delta x over 2 here, right? So we apply the heat equation from convection to node number 1. So you have H, so which is this area I've already explained. So this length here is only delta x over 2, and then we have heat transfer T infinity minus T1. So you get this equation, right? Now next is we are considering from node 2 to node 1. So node 2 to node 1 you can see here. So this is only conduction. So for conduction the equation is Ka dt over dx. So we have the value K given to us, right? K. Now area again, so you got to consider, imagine a 3D area. So this is the area. So you need to know this length. So this length you know is delta y over 2, right? As mentioned, this is B. So we assume B is 1 meter. So times 1. T2 minus T1. T1. So T2 minus T1 and then divided by this length. So what is that length? Delta x. So because delta y and delta x are same, so you can cancel them out like this. So once you're done with that, then we need to consider for T4 to T1. So for T4 to T1, so again it's a conduction equation. So we have K times with the area. So the area is this line, which is delta x over 2, T4 minus T1, and then this length here. So this length is delta y, right? And then these two you can cancel out and you get this equation. Then remember we had heat generation. So here they have used this equation. So heat generation is this symbol, but for this they've used this. Now heat generation again, if you remember, the unit is watt per meter cube, right? So we need to now change it to watt again. So watt per meter cube, if you want to change it to watt, you must multiply with meter cube again, so that you can cancel this, you get watt, because all these values are in watt. This is also in watt, this is also in watt, this is in watt per meter cube. So we need to multiply with meter cube so that we can cancel this out. So the only way to do that is you get the volume. So to get the volume, so you need to multiply this with this length with this length. So we know this length is equals to 1, so we just multiply the element of this, and these two are nothing but delta x over 2 times with delta y over 2. So multiply with the heat generation, right? And that entire thing is equals to 0. So you substitute everything and you will end up with this equation. So I suggest that based on the explanation and based on the example given here, why don't you try it on your own, see whether you are able to get this. Now remember, we have 9 nodes. This is only the first node done, right? So the second node. So second node again is half a node. So half a node, we have to use energy balance, right? So we have convection coming in here, conduction coming in here, conduction coming in here, conduction coming in here. So for convection again, H, our A is based on this. Imagine this as another surface. B is 1, so times 1, right? So this entire thing is delta x. And then because heat is coming in here, T infinity minus T2. So that is done. And then we see from here to here is conduction. So we have K, and this is the area that we want. So this is delta y over 2 times 1 here. So imagine the area, but B is equals to 1, we assume. So this comes in delta y over 2, T3 minus T2, right? T3 minus T2, and then you need to know the length. This length is delta x, because it's coming from 3 to 2, so we take this length. So that is done for this. Then plus, now next is from node 5 to node 2. So node 5 to node 2 is conduction, K, and then we take this area, right? So this area, the entire length delta x times B, which is 1, T5 minus T2, and then this length here is nothing but your delta y. You can cancel them because they are same. And finally, we find this heat conduction. This heat conduction is also K. We have this area, which is delta y over 2, T1 minus T2 divided by, if you see, this length is nothing but your delta x. So that gives you that. Now remember, we have heat generation. So heat generation, we must multiply with the volume. So this length here is delta y over 2. This length here is delta x. And then this B here is 1. So you're supposed to times with B, but B is equals to 1. So you don't see that here. And that gives you the heat generation part. Substitute all the values and you will get this for the node number 2. Alright. Let's look at node number 3. Node number 3 again, you have heat transfer coming in here, 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 and here. Now if you notice from here and here, they are both heat convection. So this is your delta x over 2, which is given here, and this is your delta y over 2, which is given here. And both are from the convection. So T infinity minus 3, T infinity minus 3. So you have lumped it up together for both the directions. Alright. And then for T6 to T3, so T6 to T3 is conduction. So we use the same formula again. So K, so our area is this. So delta x over 2 times B, which is 1. T6 minus T3. And then this is our length, which is delta y. And we have another one which is from 2 to 3. So we have K, and this is the area, delta y over 2, T2 minus T3, and this is the length that is traveling. And this entire length is nothing but your delta x. And remember, we have heat generation. Heat generation, you must multiply with volume. So volume here means this length, delta y over 2 times delta x over 2, with this length, which is B equals to 1. and that will give you this equals to 0. Substitute all the values, you should be able to get this. So that is node 3. Now remember node 4. Node 4 is basically a half a node, and then you have insulation. So you use a mirroring technique. So a mirroring technique, you reflect this to this side, the full node. So because you get a full node, you get to use the equation. Remember T1 plus T5 plus T10 plus T5 minus 4. And then remember the equation for the heat generation. Q delta X squared over K. So substitute that, right? And you will get this equation. Right? So L is nothing but either your delta X or your delta Y, because both are same. And K is known, right? So substitute and you will get this equation. So that is done for node number 4. Node number 5 is automatically internal node. So you take T2 plus T4 plus T11 plus T6 minus 45, and then don't forget your heat generation, right? So this is from, you can look at the earlier equation. So it's written as Q delta X squared over K, right? So it's just that a different symbol is being used here, and that is equals to 0, and you will end up with this equation. So that is node number 5 done. Now, node number 6 is special. So node number 6 you can see here. So this is the node number 6. So you got heat transfer coming in here, heat transfer coming in here, heat transfer coming in here, heat transfer coming here. That means you got node 3 to 6, 5 to 6, 12 to 6, 7 to 6, and not forgetting the convection coming in from this both sides, right? So you will have 1, 2, 3, 4, 5, 6 equations, right? So this one is convection, this is also convection, and these are all conduction. So if you apply, so this 2 takes care of your convection because it's coming from both sides, and then this is from T7 to 6, T12 to 6, T5 to 6, and T3 to 6. And then not forgetting our heat generation. So heat generation here is 3/4, because this is 3/4, right? 3/4 of the whole node. So you can put 3/4 delta X times delta Y, right? So that will give you this equation. Do the same thing for node number 7. So node number 7 is this way. You have heat transfer here, here, and here. So from here is convection. So that is given here. For node 8 to 7 is conduction. So you have this equation here. Node 13 to 7 is this equation. Node 6 to 7 is this equation, and not forgetting our heat generation. So heat generation here, this is half a node. So delta X times delta Y divided by 2. So you will end up with this equation. And similarly, this is also same with node number 7. So you have heat, conduction, convection here, conduction here, conduction here, conduction here. Substitute, you should get this equation. And finally, node number 9. So for node number 9, you have convection coming in here, you have conduction, you have another conduction, and here what you are getting is heat flux, right? So we'll look into this one by one. So convection is from here. So this is your convection H. This is delta X over 2, right? T infinity minus T9, and then from here is this part here. So this is conduction K. This area is delta Y over 2 times B, T8 minus T9, and this length, which is delta X, right? And then 15 to 9 is also conduction. So we have K, and then this is the area. This area here is half delta X over 2, T15 minus T9, and then this length here is nothing but your delta Y, right? And not forgetting our heat generation. So this is half delta Y over 2 delta X over 2. So you get this times with your heat generation. Now this one here is your heat flux. So your heat flux is nothing but dot, and the unit is watt per meter squared. Now if you want to change watt per meter squared to watt, you must multiply with meter squared, so that you can cancel this to get watt. So we have no choice but to multiply with this with the area. So to multiply this with the area, so this is actually delta y over 2. So this is the length. So your heat flux is coming in here. So this is delta y over 2. And then you times with the length b equals to 1. So that will give you this. Right? So all you need to do is your heat flux times with this length, and that will give you the heat transfer that you're looking for. Add all the values in, and you should be getting this. So now you have 9 nodes, you have 9 equations. So how are you going to solve this? So 9 nodes, 9 equations. So these are your 9 equations, right? So you can actually either use a software MATLAB, or you can also solve this in Excel. Learn how to solve all these 9 equations. So what I want you to do is, I want you to basically try to get all the answers for node number 1 to node number 9 as shown on this. Make sure you understand how you solve the problem for finite difference technique. So see that you are able to get this on your own. It's easier to see the example that is given here with all the working, but once you start doing it, you will know that it's not that easy. So try to work it out on a piece of paper on your own. Try to solve the same problem again. Get these 9 equations, and then try to use either MATLAB or Excel. If you don't know how to use Excel, just Google it, how to solve matrices using Excel. It will give you some idea. So you can convert this into matrix, right? And then solve it, and this will give you the answer as this. So see that you are able to get this answer, right? So use MATLAB or Excel, try to solve, and then that will be the end of our finite difference technique class. So hopefully you have understood it. I'll give you some questions for you to try, and then you can apply the same method here to solve problems in what do you call that, the questions that I'm going to give you. But again, those will be restricted to only either 3 or 4 nodes. But bear in mind, in actual practice, you don't even get 9 nodes, you get more than that. It's roughly about few thousand or few 100,000 nodes. Now you can even go for millions of nodes. All right. So to do that, you need to learn computer programming. So with that, we end our finite difference time. And this is the graphical solution that you will obtain when you plot it with the answers that you've obtained.